Next, our speaker is Liam Moshovelis. Sorry, I'm sure I pronounced your name wrong. Um, and you will be speaking for Williams, I believe.
Right. I'd like to thank the event organisers for allowing us to present our research. So my name's Liam Moshovelis, and I'll be presenting simulations of radiation shielding materials on the Lunar Gateway. I'd also like to acknowledge the work by Maggie Williams in this research. So the objective of our research is to characterise the ionising radiation environment on board the Lunar Gateway and to investigate applicable ionising radiation shielding techniques in order to enable longer duration crewed missions in space. So of the three major sources of ionizing radiation, our main interests are in solar energetic particles. And this is for two main reasons. Firstly, is the gateway will be in orbit around the moon outside the protection of Earth's magnetic field, and therefore will be subject to much higher radiation doses from solar energetic particles than its predecessors in low Earth orbit. And secondly, the crewed missions for Artemis are expected to begin towards the solar maximum of Sun Cycle 25. The primary particles are not the only work for our astronauts. As the primary particles move through the spacecraft, they'll produce a number of secondaries, including protons, neutrons, gamma rays, pions, alphas, electrons, and heavier ions. And these are produced through a number of processes and interactions, which I won't have time to go through today. But they're very important when designing radiation shielding, and we must first understand what particles there are inside and what energies and what damage it can do to the astronauts. So in situ resource utilization will be very important for the Artemis missions, and for this reason we have chosen to research lunar regolith as a radiation shield on board Gateway. More specifically, the highlands composition, which we have estimated to be similar to the composition found at the South Pole. And as a comparison, we're also researching the shielding with polyethylene and water, which have been proven in previous research to be effective against shielding ionizing radiation. So for our research, we've used an application called ASPIRE, which stands for the Assessment of Spacecraft Ionizing Radiation Environment, which is being developed at RMIT University. So ASPIRE can be used to study complex space radiation problems. It utilizes the GEANT4 toolkit. It's capable of simulating high fidelity geometries and materials. It can recreate the secondary radiation environment, and the dose quantities calculated reflect the relative biological effectiveness by all radiation types on organs and tissues. So I'd like to give a brief overview of the methods incorporated into ASPIRE. So the first step is to generate a geometry and assign it materials. So this figure here shows the Lunar Gateway model developed in SolidWorks, which was then imported into ASPIRE. It has aluminium outer hull, aluminium inner pressure vessel. The interiors have also been modeled as homogeneous low density blocks composed of aluminium, copper, plastic, and composites. So we've had to make several approximations as the dimensions and materials for Gateway are not publicly available, but we've based a lot of our approximations on the International Space Station. So we've simulated an isotropic environment around the Gateway. The particles spawn on the outer surface of a sphere, which is large enough to encapsulate the entire vehicle. And we have simulated the proton flux as seen on this figure on the right, which shows the differential flux of protons for a one-year mission in lunar orbit. This data was obtained from SPENBUS particularly the ESP psychic model. So habitation module 2 was identified as a high-risk area requiring additional shielding. And for this reason, we've placed 6 2x2 meter shields on the interior that function as a SEP storm shelter. The thickness of these shields has been adjusted, as you'll see in some of the results. So this bar chart on the left shows the total energy deposited in the detector in habitable module 2. And the orange shows no shielding, the green with lunar regolith, blue with polyethylene, and brown with water. So in this scenario, the shielding was 2 millimeters thick and the volume remained constant. So lunar regolith has a higher mass. And we could see that it has the largest reduction in energy deposited by approximately 9.9%. The downside, though, is there is increased contribution from secondaries, including neutrons, electrons, and gammas. So this figure on the left shows the effective dose equivalence as a function of energy without shielding, now with 5 millimeters of lunar regolith and with 20 millimeters of regolith.
About
This
2 minutes
equates to,
left.
okay, no worries, 360 kilos and 1.4 tons. So with 5 millimeters of lunar regolith, there is about a 21.8% reduction in effective dose, and with 20 millimeters, about 46%. And we can see that the proton energies that contribute most to dose are between around 20 and 100 mega electron volts. So lunar surface missions for Artemis could involve collecting lunar regolith as for radiation shielding research. Hermes and other dosimeters on board will enable the validation and verification of simulations such as these of the ionizing radiation environment on Gateway. And what we've found so far is that lunar regolith is more effective per unit volume, but less effective per unit mass compared to polyethylene. And it also produces more secondaries such as neutrons and gammas, particularly as the thickness increases. So there's a lot more work we'd like to do to complete this research, and this will involve simulating the alphas and heavier ions. We'd like to simulate a larger variety of thicknesses in more locations on Gateway, and we'd also like to determine the cost saving by using lunar regolith as opposed to launching to the equivalent mass of shielding from Earth. And lastly, we'd also like to investigate how it performs in the GCR environment. I'd like to acknowledge my supervisor, Dr. Gail Iles, and Maggie Williams for a contribution to this research. Thank you all for listening.
Thanks. Great presentation. I don't see any questions in the chat right now, so I will ask when you've shown your you use the gateway as kind of a place to kind of look at this. Have you considered looking at what a habitat on the lunar surface would be, since you'd be wanting to use lunar regolith there? And I believe there has been some work looking at using 3D printers to help with some of that construction, or at least as a possibility. So have you considered using that as a place to start and looking at what would be needed for shielding there instead of the gateway itself?
No, we haven't looked at the surface. I've noticed there's quite a bit of research already going into creating or using regolith as shielding on the surface. So we tried to differentiate ourselves and see what effect it could have on Gateway. But it is an area of interest that we might look into in the future.
Cool, cool. Very interesting.